This meeting is being recorded.
In this next section of chapter 16, we're going to take a look at weak acids now. So up until this point, you've probably only thought in terms of strong acids where we measure their strength on a pH scale. So the pH scale is generally reserved for the strong acids. So now we're going to think in terms of pKa, where we see over here at the top of this table that every weak acid has a corresponding acid dissociation constant. So that's what this Ka value is, our weak acid dissociation constant, and that's given over here in this column. So we can see that the larger number, so for chlorous acid, HClO2 here, would give us one of the stronger acids on this list. So when we take the negative log of this Ka value, we would get the lowest pKa value overall. The lower the pKa, the stronger the acid. So keep that in mind. When we find pKa, the lower the pKa equals the stronger. But initially looking at the Ka values, the greater the value of the Ka, the stronger the acid. So what that means is that this thing that ionizes to the -2 power, much more than something down here, would mean that this acid dissociates more, ionizes more, and therefore is more acidic. So chlorous acid is the strongest on this list, and then we have HF, hydrofluoric acid, nitrous acid. Be careful not to confuse these two with the strong acids because they do have Ka values over here, meaning that they do not ionize 100% in aqueous solution. So let's take a look at, say we're given a Ka value, or we're given pH rather, and we wanted to find our acid dissociation constant. We can do that. So how can we do that? That's what we're going to see right here with sample exercise number 10. So we're told that we have a solution of 0.100 molar formic acid. And here's the formula for that, just so we can write out this dissociation. So we have HCOOH, and we know we add that to H2O. And then we get this equilibrium established here. So we're going to have our formate ion, COOH, and then we're also going to get hydronium on our product side here. So this is our acid dissociation. And if you recall, our weak acid dissociation constant is going to be a ratio of the products. So our formate and then hydronium up top here. And then we're going to divide by our initial weak acid concentration. So let's see what this looks like. We're going to use a technique here called an ICE table. And so you may have seen this in previous examples in other chapters. When we needed to find equilibrium concentrations, say for pressure, concentration, we'll use the same technique. So what are we given? We're given 0.1 as our initial concentration. So we'll plug that in there under our formic acid. And initially we have none of this product nor this product. So let's move along. Using the balanced chemical equation, we see that for every 1 mole that we lose of this, so we'll indicate that with the variable x and say -1x, we get +1x of each product. So our equilibrium concentration will be this, 0.100 minus x, and then over here we'll get x and x. So now we're going to plug in these equilibrium values to our equation. But before we do that, we can actually solve for x here because we're given the pH. So we know what x is, what this hydronium ion concentration is. So let's do that. 10 to the negative 2.38 will give us a hydronium ion concentration, our x value, equal to 0.0042. So that's our x. So now when we plug this in, we'll see that our top values here and here, those would both be 0.0042. So we can just square that. And then down here, we'll do 0.100 minus 0.0042. All right, so make sure you plug in that 0.1 minus 0.0042 in the denominator. When we plug all these values in, we're actually going to be able to find our acid dissociation constant, and we find this to be for this acid about 1.8 times 10 to the negative 4.